Right, approximation. So for approximation, we're all about, I can skip all that. We're all about function approximation. We want to learn some kind of function without, I don't even know where I was going with that sentence. Basically, we want to approximate a function. That's really it. And this is a type of supervised learning problem. An example of that would be this one, where we have some kind of robot and it has legs and we want to move, right? We have a very continuous action space. We have some limits for that action space, but still continuous. What else do I want to mention? A little bit about Q learning. That's fine. That's just review. Yeah. So the reason we talk about Q learning is because if you had Q learning for a problem with a large action space, you would definitely run out of memory. You can't possibly represent a continuous space with a table. You'd never have enough entries. Also, you'll likely never re-encounter particular state action sequences. What else? Yeah, and because of that, you'll have to generalize since you won't see the same state actions over and over. So with a limited experience, you have to basically generalize to a larger subset of the state space. And that's where we're trying to bring in function approximation. So for the most part, our functions will be written like this, v pi being the true function, and then v hat being our estimate. In some other classes and textbooks, they mention the true function as v star. That's totally okay. So you can perform function approximation with a linear function, but for the most part, you'll see more ingenious approaches happening with a neural network or a decision tree, so a more complicated machine learning approach. This is an example of a linear function. Nothing special happening here besides adding and multiplying. This is an example of a 2D grid world where we have 16 squares and 2 of them are unlabeled. The question is really, how can you represent this based on an encoding? Similarly, if you had like air quality for a couple days, how would you represent the state space with features? Or how would you encode basically the states of the air quality? These are some examples of how you might want to do that. So like those are more concrete examples, but now if you're given numbers instead, how would you go about approximating the function? Question. So if you were working with the Q table, then you'd have this many entries, but if you have a weight vector, then you'd have only the size of the number of features. So definitely a lot more memory intensive if you have a Q table. Okay, yeah, you want to basically reduce your loss. That's kind of the heart of machine learning at the end of the day. And reducing loss is a minimization problem. So now you do gradient descent. Yeah, so when you do gradient descent, you can do it in batch where you compute the loss for every state, or you can do stochastic where you can update weight parameter for one state at a time from one sample. Damn, I got that question wrong in the exam. So the reason you want to use stochastic instead of actual gradient descent. Wait, hold on. Yeah, batches. Yeah, this is probably just general stochastic general gradient descent. So yeah, it's compute friendly if you do stochastic. Yeah, I got that question wrong. Yeah, again, gradient descent, not a big deal. Gradient descent now applied to MC. So you're basically modifying your weight parameters by finding the delta between the sampled return and the current estimate of the value of the state that you're looking at. So that's pretty cool. Tabular versus gradient MC. Do I remember the answer? For tabular, you need one entry for every state, and then gradient, you just have the size of the weights. What is updated? Everything is updated, because if the entire weight vector is modified, then all the values of all the states are modified, essentially. Again, target values. I think this is where we talk about the update equations a bit more. So previously saw that we were using GT, now we're using a bootstrapped estimate, and now that makes this a TD type approach. Oh, this is a prediction. Yeah, this is prediction. That's fine. Yeah. So you got that question right. Again, linear approximation. In this case, if you try to get the gradient of this function with respect to its weights, it would just be the original feature vector x. Yep. What is this? Oh yeah, try to compute MC prediction values. Yeah, that's not too bad. You can just run this algorithm up here. Where is it? On that data for that particular episode. You only have one episode, right? You have 11823 and then 12814. Just run MC prediction, and then you'll get two values for each state. Sorry, one value for each state, and then you have two states, so two values. You could do this by hand, no problem. Semi-gradient sources. So yeah, if you wanted to now take this modification that was done for TD and try to do for SARSA, you can get something that looks like this. Yeah, that update equation right there. I can't highlight it. What are the benefits of approximation? Yeah, you basically end up modifying the entire state space. Sorry, modifying values for the entire state space, and then I have no idea what that is. Benefits of approximation. Wait, did I? Yeah, QSA will be updated. Yeah. Feature construction. So this entire idea of linear approximation relies on good feature construction. So course coding is the way to go. And I think that should be it for this slide deck. Oh no, policy gradient methods and approximate solution. So when you put them together, what does it look like? So that's reinforced with baseline, as we've seen in the last slide deck. Where does this take us? Actor critic again. I don't think anything new is mentioned here. Yeah, that's pretty much it. Highlight of this particular slide deck would be... Should I just say gradient MC? I think I can go with any one, but gradient MC since it shows up first, because the idea is that we're modifying the function approximation like that. Yeah, I'll leave it at that. Cool.